Hi guys, I'm Jody. Thank you so much for coming to this session of talks. I'm really excited. We've got two really great talks lined up all about funky graph coloring, so get excited. Our first speaker is Reem Mahmoud, and she will be talking to us about Kempe equivalent list colorings, and she's from the Virginia Commonwealth University. So please make Reem feel welcome. Reem, over to you.
Okay, thank you for that introduction. So as mentioned, I'm going to be talking about Kempe equivalent list colorings. I probably won't be able to say too much about the result that we have for this talk, but hopefully, I'll give enough of an introduction to the problem for it to be interesting. And this is joint work with my advisor, Daniel Cranston. So let me start by defining a couple of things, really defining the terms that you see in the title of this talk. So the first thing I want to define is what we call a Kempe swap. So an alpha beta Kempe swap exchanges the colors alpha and beta on a component of the subgraph induced by vertices colored alpha and beta. So let's take an example to see exactly what we're talking about. So here we've got the garage graph, and we have some 5 coloring of our graph. And let's say I wanted to perform a red-blue swap on this red-blue Kempe swap on this coloring. So first I would focus on the subgraph that is induced by vertices colored red and blue. So that would be this whole path right here and also this vertex. So my subgraph has 2 components. And when we want to perform a swap, we would perform it on just a single component. So let's say I pick this component to perform the swap on. And so now all I have to do is I just swap the colors on the vertices, and I get a coloring that looks like this. So that was a red-blue Kempe swap. Now let's say I wanted to perform another red-blue Kempe swap, but now I pick this component. And so again, I swap the colors on the vertices. In this case, it's just a single vertex. So I'm really just going to recolor it with blue. And I get this coloring. So the nice thing about Kempe swaps is every time you perform a Kempe swap on some proper coloring of your graph, you just get another proper coloring of your graph. So now we say that 2 K colorings of a graph are K equivalent if one can be obtained from the other by a sequence of Kempe swaps. So if I can get from one to the other just by performing a bunch of Kempe swaps, then those 2 K colorings are K equivalent. The other couple of terms I want to define are related to list coloring. So let me first define what a list assignment is. So a list assignment L assigns a list of colors to every vertex of your graph. So here's our graph, an example of a graph here. And as you can see, I've assigned a list of colors to every vertex. So this is a list assignment. Let's call it L. And if every list has size K, then we say that this is a K assignment. And if every list has size equal to the degree of the vertex, then we say this is a degree assignment. So in our case, this is a 3 assignment. Now, an L coloring is basically a proper coloring of your graph where every vertex is colored from its list. So this coloring that you see right here is an L coloring of a graph. And now we can define something that's sort of analogous to Kempe swaps, but in the context of list coloring instead of just coloring. So we say an L valid Kempe swap is a Kempe swap that produces an L coloring. So it's the same idea as before. You're going to swap the colors of some component, but now you have to make sure that when you perform the swap, you still get another L coloring of your graph. So basically what that means is you have to make sure that every vertex is still colored from its list. So for example, if I wanted to perform a red-green swap on this coloring right here, right, focus on the subgraph induced by vertices colored red and green, that's just going to be this edge. There's only one component in this case. So, right, swap the colors on the vertices, and now every vertex is still colored with a color from its list. So this is an L valid Kempe swap. But let's say now I want to perform a red-blue Kempe swap. So this would be my component. I would swap the colors on the vertices, but now this vertex is colored blue, which is a color that is not in its list. So that would be not an L-valid chem swap. And so now we can define also something that's analogous to K equivalent, but again, in the context of list coloring. So we say that two L colorings are L equivalent if one can be obtained from the other by a sequence of L valid chem swaps. So again, right, if I can get from one to the other just by performing a bunch of L valid chem swaps, that means my two L colorings are L equivalent. Okay, so now let me say a few things about sort of what we know about the equivalence of colorings for graphs. So Lesvernus and Maniel proved that if G is D-degenerate, then all D+1 colorings are D+1 equivalent. As a reminder, graph is D-degenerate if every subgraph of G contains a vertex of degree at most D. Particularly, this means G itself contains a vertex of degree at most D. And this vertex turns out to be sort of a nice vertex that helps us prove this thing. So the proof for this is not super hard. It goes by induction on the number of vertices, right? So you're trying to show that all D+1 colorings are equivalent to each other. So you take two arbitrary D+1 colorings, and then you want to delete this sort of special vertex of degree at most D. And then you take the restrictions of those two colorings that you started with onto this smaller graph. And you say by induction, there's a sequence of chem swaps that takes you from the first restricted coloring to the second one. And then you sort of try to lift the sequence up to get a sequence in your original graph G. And everything sort of works out because the vertex that you deleted had degree at most D, and you're working with D+1 colors, so you kind of have an extra color to work with. So that's the very hand-wavy argument for how this works. And then after that, Mohar conjectured that all K colorings of K regular graphs are K equivalent. And Fali, Johnson, and Polsma showed that Mohar's conjecture is true for K equals 3, with a single exception, which is the Cartesian product of K2 and K3, which is basically this graph that you see over here. So for this particular graph, which is a 3 regular graph, there are 3 colorings of this graph, which are not equivalent to each other, mainly those two that you see right here. And I'll let you stare at it and figure out for yourselves why that is the case, or you can just ask me at the end of the talk. And so after this, Bonamy, Bousquet, Fali, and Johnson basically just took care of all the other K values. So they showed that Mohar's conjecture is true for K greater than or equal to 4. And so if we combine those two results, Mohar's conjecture is true with this single exception. And so for our result, what we wanted to do is we wanted to prove something analogous to this statement of Mohar's, but in the context of list coloring. So before I state what our main theorem is, let me define a couple of things. So if we have a list assignment L of our graph G, we say that G is L swappable if all L colorings of G are L equivalent. And we say that G is K swappable if it is L swappable for every K assignment L. And similarly, we say it's degree swappable if it's L swappable for every degree assignment L. So again, let's take a very simple example to illustrate this. So let's say here, our example, our graph is just a single edge. And I've given my graph a 2 assignment. So let's call this assignment L. And if I can show that all of the L colorings from this assignment are equivalent to each other, then that means my graph is what we call L swappable. So those 2 colorings are the only possible colorings from this assignment. And I can easily show that this one's equivalent to this one just by performing a red-blue swap on this edge. So that means they're equivalent to each other. And so my graph is L swappable. But now notice that this 2 assignment is not the only 2 assignment that I could give to my graph. In fact, for this very simple graph, I only have 3 options. Either the lists have an intersection of 2, so they're identical like this case, or they have an intersection of 1, or they have an intersection of 0, so they're disjoint. So for example, if we take the second case where they have an intersection of 1, again, right, let's say we call this list assignment L. Again, if I can show that all of the L colorings from this list assignment are equivalent to each other, then that means my graph is L swappable. So those are the only possible colorings. And I can show the first one is equivalent to the second one by performing a red-blue swap on this vertex right here. And then I can show that this one's equivalent to this one by performing a red-to-green swap on this vertex. And then sort of by transitivity, this top one is equivalent to this bottom one just by going through this sequence of chem swaps. So again, my graph is L swappable. And you can sort of, I didn't put it here, but you can check for yourself with the last possible list assignment where the lists are disjoint, and convince yourselves that it's going to be L swappable again. And so that means that my graph is L swappable for any 2 assignment that I give it. And so now I can say my graph is 2 swappable. So now that we have this, let's state what our main theorem says. So our main theorem says that for k greater than or equal to 3, if G is a connected k-regular graph, then G is k swappable, again with this single exception of this graph right here. So notice, right, this is just the same statement as Mohar's, just stated in the context of list coloring. One thing I guess to note is we can replace k swappable in the theorem by degree swappable, just because those mean the same thing when we're working with k-regular graphs, right? K swappable means we were working with lists of size k, and degree swappable means we're working with lists of size equal to the degree of the vertex, which will be k if we're working with k-regular graphs. Okay, so how do we go about proving our theorem? So our theorem relies on this key lemma, which says the following. If H is a degree swappable graph and G is a connected graph containing H as an induced subgraph, then G is also degree swappable. So basically what this is saying is if the big graph you're trying to show is degree swappable contains a smaller graph that you know is degree swappable, then that means the big graph is also degree swappable. And so I won't go into the details of the proof of this lemma, but it follows a similar idea as the proof that I mentioned over here of philosopher and Menial. And so how are we going to use this lemma? So here's the idea of the proof. So the first step we're going to do is we're going to try to compile a set of small graphs that we can sort of easily show are degree swappable. And then we're going to show that our big graph, the one we're trying to show is degree swappable, the k-regular graph, must contain one of these guys as an induced subgraph. And so obviously now we can use the lemma to say that means our big graph is also degree swappable. So most of the work of the proof really happens in this second part. So I will not be going into the details of that for the sake of time. But I will tell you a little bit about what sort of graphs we compiled and the small graphs that we showed are degree swappable. So let me first say that this idea of the proof is very similar to the idea that was used to characterize degree choosable graphs. So if you are not familiar with degree choosability, a graph is degree choosable if for any degree assignment that you give to your graph, there's some proper coloring from that assignment. And so Erdos, Rubin, and Taylor characterized all the graphs that are degree choosable. And I won't go into the details of the proof, but basically they used a similar technique that we're doing here. And so they compiled a list of graphs, small graphs that they easily showed are degree choosable. And really in their case, it was just a single graph, which was this even cycle with at most one chord, which we're going to call a good cycle. So naturally, when we thought about this, we thought, maybe it's a good idea to start by showing that good cycles are degree swappable. But it turned out that cycles in general, let alone good cycles, are not degree swappable. So here's an example of a cycle. Here we've got a 4-cycle, and we've got a degree assignment of our cycle. And those are 2 different colorings from that degree assignment. And those 2 colorings are not equivalent to each other. And you can sort of see this. So if we try to perform any swaps to get from this coloring to this coloring, let's say I wanted to perform a red-green swap, right? This would be my only component. I would swap the colors on the vertices, but now this vertex would be colored green, which is not in its list. So that would not be an L valid chem swap. And you can try this with sort of any pair of colors, and you'll see all the swaps will not be L valid chem swaps. So there's no way to get from this coloring to this coloring using L valid chem swaps. So, that was a bummer, but turned out that if we take 2 good cycles and we sort of join them together with a path, then that is a degree swappable graph. So here are all of the graphs that we showed are degree swappable. So this first one is what we call a K4 plus, which is basically a K4, but then you take one of the edges and you subdivide it as many times as you want, so you get this log path. Another one was a 4-wheel, so this is a 4-cycle with a vertex in the middle that's adjacent to everybody on the cycle. And this is what I mentioned, which is 2 good cycles that are joined together by a path. And this path can have length 0, so that means just this vertex and this vertex are just a single vertex joining both cycles. And finally, a bipartite theta graph. So as a reminder, a theta graph is a graph that has 2 degree 3 vertices, and they're sort of joined together by 3 disjoint paths that can have any length. But when we talk about bipartite theta graphs, we can't have odd cycles, so the parities of the lengths of the paths have to be the same. So that is all I'm going to say. Here's a very short summary of the points I mentioned, which is not a lot. I had to sweep lots of details under the rug for the sake of time, but here's a nice QR code of our paper in case you want to look at all the details that I didn't mention. And yeah, that is it. And I'm happy to take any questions.
Excellent. Can you all please join me in thanking Reem for her talk? Yeah, we'll take some questions now. So if you have a question, please pop it in the chat. Just going to scan this QR code quickly before it disappears.
I had a question. So could you just repeat the definition again of degree swappable?
Yes.
Just wanted to.
So here it is. So degree swappable just means for any, or I guess the graph is L swappable for any degree assignment L. So basically, if you give your graph some degree assignment and you take all of the colorings from that assignment, all those colorings are equivalent to each other.
Okay, because just in terms of understanding the intuition of your main lemma. So with the degenerate argument, in that case, it's like more of a global structure going on, because you can always remove a low degree vertex. But for your main lemma, it seems to be very much like a local property. Like there's just one single induced subgraph in that connected blob that has that property, but it doesn't say anything about the rest of the graph. And so, yeah, it seems like quite strong. And so can you sort of like maybe a bit more intuition surrounding that in terms of there seems to be very much like a local property that's getting lifted to something globally, where degeneracy is more the global property.
Okay, so I know I stated this theorem of Lassernes and Manuel as relating to degenerate graphs, but really they proved a much stronger statement, which is you just need to have this vertex of degree at most D for everything to work out. So if your graph is degenerate, you just get this vertex for free. So that's sort of like I guess a corollary, if you will. of their actual thing that they prove. And so our lemma, I guess, is more coming from this idea that I mentioned, the disproof of degree choosability. So they did a very similar thing where, again, they had this, this is the only, I guess, small subgraph that they had, this good cycle, and they could easily show that that's degree choosable, and then they showed that their big graph must contain this thing, and then they showed that that's sort of enough to sort of extend whatever coloring they have in the graph minus this thing to the whole graph, basically. So really the intuition behind this was coming more from the technique of this proof, but the overall, I guess, idea of like, so the way this lemma works is you do something very similar to what they do over here, which is you delete this subgraph that you have, and then you get a sequence for your smaller graph, and then you lift that sequence up to get a sequence in your bigger graph. So the proof is kind of similar to this, but the idea is sort of coming from this thing.
And then another question I did have, so I guess with the degeneracy result, that would apply to a lot of graphs like planar graphs. And so in the normal coloring section, could your result here also apply to, say, planar graphs, or is there much known about already about Kempe chains with list coloring of planar graphs?
So, so I kind of lied a little bit, or I guess I didn't say the full truth with our main result. So I stated it in terms of sort of K regular graphs, but actually this, our actual result says something like, for delta greater than or equal to 3, if G is connected, is a connected graph, then it's delta swappable with, again, this, this exception. And then this goes back to, so it's more than just, K regular graphs. It works for, as long as you're taking the maximum degree as like the size of the list, then it works for the exact same reason as this idea of less fairness and menial. You just get, if your graph is not regular, you're going to take this vertex that has degree that's smaller than delta, and then everything works out. Otherwise, it has to be regular, and then this is where our theorem comes in. I don't know if that answers your question.
We have a question from Angus in the chat. So Angus says, could you use these Kempe swaps to do things like approximate counting or approximate random sampling of graph colorings?
Yes, great question. So yes, that is, so if I had more time, I would have talked more about this thing is sort of part of a bigger class of problems called reconfiguration problems. And the idea is all these colorings become sort of vertices in a bigger graph, and they're adjacent if you can get from one to the other through some Kempe swap. And so you can definitely use this to do this sort of approximate sampling or counting, sort of to enumerate, instead of enumerating all of the graphs, we approximately enumerate, or all the coloring, sorry, of your graph. So yes, that is exactly what these types of things are used for.
Awesome. I have one more question. So in your last slide, I think you said something like cycles are not degree swappable.
Yes.
Yeah, this one. So I'm still a bit confused about this. Is there sort of an easy explanation or an intuition behind why cycles are not degree swappable?
So maybe, I don't know if it's like, probably because I used colors instead of numbers, it might be more apparent with numbers instead of colors. But basically what I'm doing here with this list is I'm sort of doing like 1, 2 for this vertex, then 2, 3, then 3, 4, and then 1, 4. And so every time now you try to do a swap, your swap is going to look right. You're going to like pick 2 colors and try to perform the swap on whatever component you have, which For cycles, it's just going to be some edge. So once you perform the swap, you always end up, because of the way we've chosen the lists, you always end up with some vertex that is colored with a color that is not at its list. And so you get this problem of this swap was not valid. So that's why those cycles are never going to be degree swappable.
Awesome. That's really nice. Yeah, I totally did not pick up on that. But I think that's our time for questions. So can everyone please join me in thanking Reem again?